Hi everyone. So today we're going to talk about Gauss's theorems, which is 9.4, and surprisingly, that would be our last sections for today's for this year multivariable calculus. So I'm very excited to get started, and so hopefully you are too. So what's Gauss's theorem? So that's actually very similar to something that we have already learned, which is green theorem. So the reason why it's very similar to it is because they kind of do the same thing. So before we talk about it, let's Gauss's theorem. Maybe we talk about green theorem first, just to remind you. So a quick reminder: the green theorems basically allow us to evaluate a closed curve integral by transforming it into a double Riemann integral. Now, why is that so important? Because of the following. So before let's finish. So double Riemann integral with the regions enclosed by the closed curve. Or maybe I should use bounded by the closed curve. So the important part about green theorem, which I have mentioned to all of you before, is the following. The problem with line integral is a mismatch of differential versus the integral. Why? Because a line integral, by definition, is a single integration because you're integrating over something one-dimensional. But the problem is the curve could be actually in higher dimension than 1. It could most likely be in R2 to R3 to R4 to R5 and so on and so forth. So green theorem allow us to actually deal with a closed curve, but in R2. And what it does is allow me to fix the problem of the mismatch of differential and integral. Line integral is single integral, but if the curve is in R2, then therefore there will be two things that are changing, dx and dy. And one way to bypass that problem is to use a parameterization of the curve, which allow us to then define both x and y through the use of a parameter, and therefore allow me to integrate just through the parameter. The problem is that sometimes a parametric representation can be hard to come by. And when that's the case, you are kind of stuck. But lucky for us, green theorem allows us to work past that issue. So how does green theorem work? So imagine the following. Let's say you are on the xy plane. You have some kind of closed loop, okay, which I'm going to orient in a positive orientation. And I'm going to go and call this closed loop delta D, where the inside of these regions is going to be called D. Okay? So if I now do a closed curve integral over this boundary, green theorem suggests that I can actually do a double Riemann integral over the enclosed region by modifying the integrand, using this scalar curl of vector f. And so remember, this is basically called the boundary of the regions D. Okay? And this allows us to deal with a two-dimensional curve, a one-dimensional curve in R2 into a double Riemann integral, which is Now something that I can actually integrate twice to deal with the two things that are changing as I move through this curve. Then what is Gauss's theorem? Well, Gauss's theorem does the same exact thing just like green theorems, but a dimension up. So show you what Gauss's theorem is. So before we do that, let's talk about the following first. Let's give you some terminology first. Let's say given a closed surface. I'm going to call this closed surface S because, letter S for surface. So what's considered a closed surface? So closed surface in R3, closed surface S in R3. A closed surface in R3 would be a surface that completely encloses a solid in R3. So it's more like a surface area, a surface of a solid. Okay? So example of a closed surface. We can definitely form a sphere. Well, surface of a sphere. We could definitely have a surface of a cube. You can even have a hemisphere as long as it's completely enclosed. So a hemisphere, we have the top hemisphere and also a circle on the bottom that will completely enclose the hemisphere. If you just have the hemisphere on top without the bottom circle, then you actually don't have a closed surface. So that would form a closed surface. But without the bottom, it doesn't work, of course. And of course, we can also have a cylinder. So cylinder would be top and bottom circle. And the lateral area, the lateral surface. Then all together would form a closed surface. And of course, the surface of a cube would be like 6 square. That would be together to form that closed surface. So, interesting thing about it is a closed surface must enclose a regions in R3. And hopefully some of you seeing the parallel that I'm trying to form here with the closed curve integral. So a closed surface S in R3 must enclose a regions in R3. So in this case, what we're going to do is, what if we call these regions R? If we call this enclosed regions R, then the closed surface S will form its boundary. Therefore, R can be called, and here you go, the notation, partial dr. And notice that's the same exact notation that we use. We define an enclosed region, n is boundary. We use this partial derivative to define it to be the boundary. And once again, the idea here is that because if this region expand, it will expand by how long the boundary would be. That's the reason why the boundary kind of become what we call the differential of it. And if we integrate over this closed surface, we can call our integral a closed surface integral. So we form a surface integral over this closed surface. We have a closed surface integral. So it's kind of like the line integral and the closed curve integral. Okay? And the notation for that, shockingly, is this. Actually, here I'm going to use this notation instead to avoid the confusion with the d vector s. So the closed surface integral is usually represented as a double integral because it's a surface integral, but have a circle over in the middle, which represent the closed surface. Okay, so kind of like the closed curve integral. As a matter of fact, if you write a surface integral with a single integration and with a circle over it, based on the way the function, the integral set up, it will be understood as a closed surface integral. So meaning in this case, I could actually use a single integral with a circle and an s on the bottom. And it will be understood as a closed surface integral because s is a surface. And the whole integration would kind of work out very similar to a closed curve integral. So now comes the big part. What does Gauss's theorem stay? Well, Gauss's theorem basically stays the same thing as Green theorems. Meaning that if we deal with a closed surface integral, we can actually rewrite a closed surface integral as a double integral into a triple integral in R3. Okay, so what Gauss's theorem allows us to do is to change a closed surface integral which remember is a double integral for a surface in R3, allows us to change a closed surface integral into a triple integral, triple Riemann integral, and in this case for an enclosed regions in R3. So that's what Gauss's theorems allow us to do. And it's fixed the problem where before we have a double integral but dealing with something in R3. Now it fixes the problem by turning into a triple integral. So how does Gauss's theorem work? Well, let's show you the definition so that you know. Okay. There you go. Gauss's theorem. So let's say we're given a closed surface in R3. And it is the boundary of a region's R. maybe I would say in a regions in R3. Let the regions be R, then the closed surface will be the partial derivative of R. So here you can think of R as like the sphere, and then the dr would be the surface of the sphere. Or R could be the cube, and dr would be the surface of the cube. R could be the hemisphere, and then dr would be the hemisphere, the surface of the hemisphere, plus the circle on the bottom. And if R is the cylinder, then dr would be the top circle, bottom circle, and the lateral surface altogether. So that's how that works. So now come to the important part of Gauss's theorems. So if I take a closed surface integral over dr of vector f dot n d sigma. So that's our basic surface integral. Gauss's theorem states that this can now be turned into a triple integral over the regions R of the divergence of f dv. So what is the divergence? So you probably remember learning it back in chapter 8. So what is the divergence of? So this is basically called the divergence of vector f. So what is the divergence of vector f? Well, let's talk about it. So let's say if f is equal to f1, f2, f3. Remember, we're only dealing with R3. Then the divergence of f is basically equal to the gradient operator dot product with vector f. And that means it's just d over dx, d over dy, d over dz, dot product with f1, f2, f3. And so what does that turn into? That turn into df1 over dx plus df2 over dy plus df3 over dz. So therefore, our Gauss's theorem basically saying that this closed surface integral will now equal to a triple Riemann integral of the divergence of f, which is basically equal to a triple Riemann integral of df1 over dx plus df2 over dy plus df3 over dz. dx, dy, dz. So that's what the Gauss's theorem is. Now, I know it might look complicated, but actually it's not that bad. So let me show you a very simple example that we have done together and show you how easy it turned out. So the example that we're going to do is actually the cylinder one, which is the first one that we did with surface integral. So let me see. I'm going to go ahead and let's see if I can copy this picture right here. Oops. Oh, okay. I think I did. Okay, let's see if I can do this. Oh, nope, never mind. It didn't copy the picture. I guess let me see if I can figure it out. Okay, hold on. I actually won't be able to copy the picture. I guess I just have to draw the picture because I didn't have the picture saved, unfortunately. So oh well. So let's do the example that we did in 9.3. So 9.3 this example. Let's say we're given vector f of xyz is just equal to xyz. And we're going to try to find this closed surface integral of dr of f dot vector n d sigma, where dr is the surface of a cylinder with radius A and height B. So I don't remember how I word the problem. Let me see. Okay, surface of a cylinder, blah, blah, blah. Okay, we also want all the normal vector pointing outward. So let me just write that in. With height B. And all normal vectors are pointing outward. And that gives us a kind of positive orientation of the surface. So we're going to go and try to find this closed curve integral. Let's see if we can do this. And this time what I'm going to do is I'm going to use Gauss's theorem to figure it out. So let's go for it. So let's see how do we do this. So before, when we without Gauss's theorems, actually let me draw the picture first. So here's my cylinder. So I'm actually going to have this cylinder. I think center on the bottom is on the origin, and so the bottom actually form the equation x squared plus y squared equal a squared, and z equal to 0, and then the top is x squared plus y squared equal to a squared, but z is equal to b. And then we have the lateral surface area. Okay, so now let's see. So I'm going to go ahead and use Gauss's theorem to calculate this. And hopefully we're going to come up with the same exact answer as what we have before. Let's hope. Unless I did something wrong. Let's hope I didn't. So in this case, what I'm going to do is the following. I'm going to first start by this. We know that vector f of xyz is just xyz. So that's pretty simple, because that tells me that this is my f1. My f1 is x. My f2 is y. And my f3 is z. So that's pretty nice. So now what I'm going to do is I'm going to apply Gauss's theorem. Based on Gauss's theorem, this is actually equal to a triple integral over R, where R is in this case the cylinder, okay, of d over dx of f1, which is x, plus d over dy of f2, which is y, plus d over dz of f3, which is z, dv. So as you can see, d over dx of x is just 1, d over dy is just 1, d over dz is also just 1. So therefore, this just all come out to be just 3. So therefore, this come out to be a triple Riemann integral over R, 3 dv. Since 3 is a constant, I'm going to pull out the 3. And now all I have is a triple integral of R dv. Well, guess what? That just equal to 3 multiplied by the volume of R. And since our regions R is the cylinder with radius A and height B, I can now say that the volume of this thing is just pi radius squared, which is A squared, times height, which is B. So that come out to be 3 pi A squared B. Let's hope that is the right answer that we have done before. Let's see. Blah, 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 blah. Oh, yeah, there you go. 3 pi A squared B. Notice that how simple it is when we do Gauss's theorem. For this particular example, I finish in like 3 lines, compared to what I did where I have to separate into 3 different surfaces and then either use the perpendicular vector or the parametric representation to come up with the surface integral for each surface and add them up. So this is a lot easier in this case. And you'll find out that for some surfaces that are distinct surfaces that enclose a region, like in this case the cylinder, Gauss' theorem will be a lot easier to deal with because you don't have to worry about multiple surfaces. For a sphere or something like that, it will be a little different. Okay? So, I would say I'm going to stop right here. The video is about 25 minutes already. I actually don't have anything else I want to show you other than maybe show you maybe a couple more examples on our next video, and then that will be it. All right, so I'll talk to you guys in our next video. Bye-bye.